So, do you think online presentation is okay? Uh, you- okay. So I'm traveling last week. So one one idea is to shift some of the weeks, a week uh, early. So then we don't have class on the last week. Or on that day, I will be in Italy, which is 3 a.m. Maybe I have jet lag. I will wake up at 3 a.m. so I can do online presentation. So do you prefer more lectures and present online, or just shift 1 week early? Shift. Shifting is good. How about you guys? Okay. Originally, this is the original schedule, but now I have to travel. So if I travel, uh, we can do this. We can shift some of the lectures 1 week early, or I can do online presentation on in Eton, 3 a.m. So Taiwanese, what do you think? Which one is good? Okay, shifting. So okay, so this is the new schedule. Okay, I will update the Google Sheet for the schedule. Okay. Last time we talked about AKT conditions, but we never talked about what. We didn't have the chance to talk about the details. I only show you the three equations. So today I'm going to talk about why KKT conditions are formulated in such a way. So let's first take a look at a simpler problem. So let's take a look at a problem like this. So only with equality constraints. And let's say there are n of equality constraints. Okay. Now, during the iteration process, let's say you develop some kind of optimization process, and let's say at the k iteration and k plus one iterations, because you need to satisfy the equality constraint. So one idea is that at the k iteration and the k plus one iteration, you want the equality constraint to be satisfied for both iterations. So you want this to happen. Right? You need both to happen. Okay? And imagine we are in a design space and there is a equality constraint. So let's say on top of this curve, this is h, some hi equals to 0. Okay? And let's say this is your design point at the k iteration. So your k at k plus 1, your x at k plus 1 may not be located at the right same position. It will be somewhere else, but you want x k plus 1 also stay on that equality constraint. So you will, by this illustration, you can then see what's going on. You kind of want to find your design point on this boundary. Okay? So from here to here, from xk to xk plus 1, you kind of make some kind of movement. So let's say your movement is d. Okay, so if that's the case, then you can formulate, you can describe the relationship between xk plus 1 and xk. So basically, xk plus 1 equals to the previous design point plus some kind of movement d, right? So if that's the case, we can then also plug in this equation to the second equation over there. So we end up with hi xk plus d equals to 0. So we have these relationships. So we may be using them later on. Okay. Now, we need to figure out one thing. Where is the location of, where is the direction of the gradient constraint? Okay, we need to talk about it. So this is something that we need to talk about in the derivation. And the next thing we need to talk about is the gradient of a constraint. Okay, so let's now talk about gradient of a constraint function. Okay, so if you again draw the curve in the design space, that's the location of that constraint function. And this is where your particular function has a function value equals to 0. So stay on this curve, your function value equals to 0. And what if you, like kind of making an offset for, let's say, left or right, okay? So these, on the other, like if you offset for left or right, you are kind of like making a drawing of the contour. Okay, so these are contour of h function. Okay, so it just happens that the solid one is the contour curve with function value equals to 0. So maybe the one on the right is contour value equals to 10, and maybe this one is contour value equals to negative 10. Okay? So if you try to figure out the direction of the gradient, it's actually perpendicular to your constraint function. So this is actually the gradient, because that's where your function value is making the change, right? What's the meaning of gradient? Right? Gradient basically is like this. Uh, let's say n. Okay? There's a vector of partial derivatives. Okay, and if you are staying on the how to prove gradient is perpendicular to the contour. Um, I didn't prepare. Okay, you can, if you're interested, you can go figure out. So maybe it's a good time for you to like think about it or ask AI about it. But the gradient vector is perpendicular to your of your function contour. Okay, so something you can think about. Function or equality constraint. Okay, so I plan not to prove it. It's basically it's perpendicular. Okay, so keep in mind the gradient of h is perpendicular to this solid curve. Okay, now with these, I then let's talk about something which is a Taylor extension of hi. Why do we need that? Because we need to derive something that indicates how your moving direction is related to your gradient. Okay, so let's try this first. So the Taylor extension of hi will look like expansion point. So let's use xk as expansion point. Okay, so here will be xk plus x minus xk dot the gradient of hi xk. Right? This is a first order Taylor extension. Okay, and let's consider x is your xk plus 1. So over here, so it's like you are investigating the constraint function at the newer design point k plus 1. Okay, so you are investigating the approximating the constraint function with the expansion point of your known information and investigating at the new position. So your extension point is this one, the original one, and you are investigating at your new point. Okay. So earlier we had this equation. We had this. So from here you can see xk plus 1 minus xk equals to d. That's the movement from previous point to the newer point. So this can then be derived as hi xk plus d dot product I x k. Okay? And since our design point will stay on your equality constraint, so this one equals to 0. Okay? And we hope our new design point also remains 0 when you move from your xk to xk plus 1. So this function value equals to 0 as well. And that indicates that you must have this unique expression, and you want this has to be 0 as well. Okay? So there's a rule called feasibility. The rule indicates that your d vector dot product with your equality constraints gradient should be 0. If that happens, your design point will remain feasible. So from a previous design point sk, which was originally on your equality constraint, and you can make a movement with d vector, but in order to move to a right position and the new design point stay feasible, you should satisfy this rule. Okay, so this is a rule for the design to stay feasible. That's why we call feasibility. The criteria for feasibility. Okay? And let's do another investigation, which is tailored expansion of your objective function. Okay? And we also investigate at k plus 1. So your objective function equals to equals to this, right? Okay. So this is the function value from the previous design point, and this is the function value at the new design point. Okay, and there's a difference. The difference between them will be the term on the right. So we are trying to minimize our function value. So what do we want? We want this value to be negative. So if this is negative, your function value at the new position would be smaller than the function value from at the previous position. Then you're improving. So if this term stays negative, you will improve your function value by minimizing, right? So here, this term, if it's negative, then function value can be reduced. So you can keep on optimizing your design. So we call this optimality. Okay? So you still have the ability to optimize your function. So if this rule stays valid, you can continue to minimize your function value. Okay, so let's now make a drawing for this. So let's say again, this is your function value hi, and then let me try to draw a contour of the object function. So let's say I have a function like this. Okay, so let's say this is the contour of f. Okay, and let's say along this direction, f is decreasing. Okay, so and let's say at the beginning, here is your xk. Okay, and from previous discussion, we already know this will be the direction of your hi, the gradient of h. So it's remaining perpendicular. Okay, and what would be the direction of the gradient of your f? So the gradient vector is gonna be perpendicular to your function contour, and gradient is the direction that. So I made a mistake here. I should draw it in the other. Sorry, the other. Gradient points at the direction with function value increasing. Okay, because if you increase x, your function value increases. So that's the direction of your function value increment. Okay, but still it's perpendicular. So right here, so h can be going this way or that way because you don't know what kind of h it is. Maybe going this way, h increases. Maybe going that way, h increases. It doesn't matter. H is perpendicular. The gradient h is perpendicular to your h. But for f, because as I mentioned, going toward the, if you say there's a center, going toward the center, function value decreases. So going outward is the direction for your gradient. So the gradient of f will be somewhere there. Okay, so this one is perpendicular, and here is perpendicular. This gradient f is perpendicular to the red curve, the contour of f. Okay, and we try to move toward this position here. So here is my xk plus 1. So we try to move like this. So this would be my D. If I do that, the D vector dot product with gradient H, because they are perpendicular, so it equals to 0. So from here you can tell, yes, they are the dot product equals to 0. So in the previous rule right here, we mentioned for feasibility, we need D dot gradient H equals to 0. Okay, how about the other one? How about D dot product with gradient F? For dot product, if it's if two vector is having an angle smaller than 90 degree, the dot product is positive. And for this case, the angle between them is greater than 90 degrees, so the dot product between them will be negative. So in this case, you can see D dot gradient F is negative. So if it's negative, it satisfies what we talked about right there. D dot gradient F is positive. So by moving toward this direction, you can improve your function value. Okay? So right here, D dot gradient Hi equals to 0 and D dot gradient F is negative. So if you move like this, you can stay feasible and you can improve your function value. Okay? So by observation, you can tell actually, yeah, your optimal solution is somewhere here. Because on this blue curve, this is the position you should have the lowest function value. Right? How about when we stay on this xk plus 1 and try to study what's going to happen if we try to move somewhere else? So the contour at this particular point will look like this. Right? So that this will be the contour for the location of xk plus 1. And if you try to investigate the gradient of h and f, you will notice that they are parallel to each other. So gradient h and gradient f parallel to each other. At this particular point. So in this case, if I try to make a move, if I try to move a design point somewhere else, if I move toward right or toward left, then I can still try to find points that stays on H if my movement is still perpendicular to H. I can do that. That remains feasibility. But when I do so, that movement is gonna be also perpendicular to gradient F. And the dot product between them will equal to 0. If that's happening, that means you're not improving. So if this term equals to 0, that means that movement doesn't decrease F. So if a movement doesn't decrease F, that's a movement that doesn't make your design better. So you shouldn't make the move. In that case, right at this point, that is showing you staying here is the best. You cannot find a better solution. Okay, then you can find. So that's where the optimal is. Okay. So by checking these two dot products can help you whether your design is remaining feasible or your design can improve your building function. Okay. So uh, one important idea right here is the gradient hi and gradient f, they are parallel to each other. So can we mathematically describe this kind of relationship? You can have a multiplier in front of one of the term and make them equal. So this indicates a new description. And right at this position, actually, your design is optimal point. Right? And this time I apply a multiplier in front of hi. This is a standard way to describe how two vectors are parallel to each other. Lambda can be positive or negative. So even they are pointing at different direction, this equation is still valid. Okay? So this lambda can be negative. So what's the name of this lambda? It's called the Lagrangian multiple. Okay. Okay. So this is the illustration with one constraint and one object function. How about in general, if I have multiple constraints, if because even though we put an index I here, but we never consider this illustration with multiple constraints. So in general, uh, how the equation is going to look like. So I forget about putting in sign. So in general, actually, the gradient of f at the optimal solution equals to sum of Lagrangian multiplier times the gradient of the ith equality constraint. And the Lagrangian multiplier, there's only one rule for it. Cannot be zero. Because the only way to make sure they are parallel to each other is that your Lagrangian multiplier has to be something not zero. Okay? Okay? So with this idea, it seems like we can investigate whether a design point is optimal or not. And we can also investigate whether a point is feasible or not with equality constraints. So this is a description, a general description. How about optimization with inequality constraints? So let's talk about inequality constraints. So minimizing f of x subject to let's see how I want to display this. Hi of x equals to 0. So I goes from 1 to n. And here I want to say gi of x, gj of x. smaller than 0, but j equals to n plus 1 to n. Okay? So how about this even more general optimization problem? Here we have inequality constraints. So remember earlier we talked about linear programming. There is a trick to convert inequality constraint to equality constraint. So what is the trick? We can do this. We can introduce slack variables. So S are slack variables. And just to make sure this portion is positive, I put a square sign right here. So this part is always positive. Then this part would be either negative or 0. Okay, so that this new equation will be equivalent to the original. But only bad thing about this is that you will have new variables, small variables. Okay, but the good thing is you convert inequality to equality. So overall, everything together, you can have hi hat of x equals to 0, and I goes from 1 to n. You can combine them, just rename them as h hat, because they are all equality constraints. And you have n of this, and the rest will be n plus 1 to n. So in total, from 1 to n. Okay? So if we can do that, we just need to make sure if the Lagrangian formulation is valid, then we should be able to check whether the design is optimal or not. So from what we derived earlier, we are trying to look for this relationship. If this is working, then this is the position, this is the x star is optimal. If this is satisfied, then your x star is optimal. Okay? This can also be written as a different format. We can also rewrite this as, so rewrite. So I move the right hand side to the left, but I still keep it as positive. Why can I do that? Because it doesn't matter what Lagrangian multiplier is. So from this to here, we just put a negative sign. So if originally is a -1, then it becomes 1 here. It doesn't matter. It doesn't matter what the Lagrangian multiplier is, as long as this equation satisfied, it is confirming your point is up. Okay, so both equation will be okay as long as you can find the proper design point which satisfy the constraint, the equation. Okay. Now I try to put what we had earlier and put everything into uh, the new equation right there. So what do we do? We can now write down the here I would like to use, I already use I and J, and we have K already. I guess I can use P. Maybe better. Okay. Let's use P. Okay. Plus summation of, so I goes from 1 to n, Lagrangian multiplier, and the first part would be partial hi over partial xp, right? And then plus another part would be I goes from, actually here, um, yeah, goes from, it's fine. I goes from n plus 1 to n. Okay? And here I will say lambda I partial gi plus s. Oh, this is where you may be confused. I think we should use j. So here we already switched to j. So here gj, sj squared over partial x. This equals to 0. Okay? So you can see that when we plug in the original h and g to this new equation, you kind of separate the equality part to a second term and the inequality part to another term. So you kind of separate. So usually we would like to uh, change the, this is lambda I from 1 to n, and this is lambda j from n plus 1 to n. So usually we would like to use different symbols to represent the Lagrangian multiplier for h and the Lagrangian multiplier for g. So usually this part they use a different name, different Greek symbols. They use mu. So for the Lagrangian multiplier in front of g, we just name it as mu. And for the Lagrangian multiplier in front of h, we use lambda. So that's the common way. But this is where I show you how it ends up with something like this. Okay. Now, how about Sj right here? If you think about it, Sj would be the slack variable you introduce for the inequality. It has nothing to do with x. So if you do partial derivative with of s with respect to x, they have no relationship. So the partial derivative between them would be 0. So this part is 0. Try to, this part is 0. Why? Sj is not a function of xt. So the partial derivative will be zero. So at the end, it ends up with the equation that you have seen last time. So this will be the first equation of KKT conditions. Okay? So that's the first equation. Now, when we do gradient, we need to do partial derivative with respect to all the variables. So here, we did partial derivatives with respect to all the x. So here, p equals to 1 to, let's say, n. This is the number of variables. But x, number of the component inside x. However, earlier we introduced si. They are also variables of the optimization problem. When you introduce them, they become our variables. Even though we don't care what the select variable look like, but they are new variables being introduced. So when you do gradient calculations, you also need to do partial derivative with respect to select variables. So let's do that. Okay? This must be 0 as well. Because right here, we need this equation to be valid. So for all the partial derivatives with respect to all the Sj, they need to be considered as well. So this is how you put everything together. And as you can see, this will be 0 because f has nothing to do with s. This will be 0 because h has nothing to do with s. This will be 0 as well because g has nothing to do with s. Only s itself has relationship with s. So this implies what? 2 times Sj mu j has to be 0. The only way this has to be valid is Sj mu j has to Sj or we describe it this way, or mu j Sj must be 0. Okay? But we don't care about s. We want to we would like to let's just keep in mind we have that particular equation. So this is equation 1, this is equation 2. and j goes from n uh, n plus one to n, based on our definition earlier. Okay, that's fine. Let's keep it in this way. We will come back to the second equation later to reconsider it in a different way, so we can come up with the second and the third rules in KKT. Now, we already talked about optimality and feasibility. This part. So we need to. Okay. We already talked about optimality and feasibility, but we never talk about the feasibility for G. Okay, so let's take a look. So let's say here is G equals to 0. Okay, and let's say it's like a wall on the left hand side. It's inside the wall. You don't want to find a solution inside the wall. The wall is your solution should be somewhere here in the upper right corner. If that's the case, then on the left lower corner, G is positive, and on the upper right corner, G is negative, right? So we always look for G equals to 0 or negative. So your solution should be either on the wall or in the upper right corner. So in this case, uh, let's now draw the contour. So this will be contour of your G. So here is with G value increasing, like where with G value decreasing. So if you have a design point right here, let's say that's your xk, your G gradient would go this way, perpendicular to your G function. Okay? And we would like to see what's the rule for feasibility. So what we're interested in is how about D gradient and then G at this is a J G, right? At the optimal. Should it be equals to 0 or positive or negative? So that's what we are trying to investigate. So if you try to move, let's say your D vector goes into the wall from your xk. Then you are penetrating through the wall. You will end up with a point that is not feasible. That will violate the constraint. So from here you can see D dot gradient of G cannot be positive, right? Cannot be positive. How about if I move toward this direction? That's my E. And if that movement is perpendicular to your, or it's at the tangent direction of your g. In that case, d dot gradient g will be 0, so 90 degree. In that case, you still stay on the boundary. So that point is still feasible. So equal sign is fine. Equal sign is okay. How about if my d is here? Because of the angle between this d and the gradient g is greater than 90 degree. So the dot product between them is negative. If I make a movement of that, I am not penetrating through the wall. I am staying feasible. It's just that I move into a safer region. That's fine for G. So that is okay. So smaller than is also fine. So this case, d dot gradient gj equals to 0. This case, d dot gradient gj is negative. This case, d dot gradient gj is positive. And this one would violate the constraint. So that is not okay. So the rule for feasibility of Gj is this. That's the rule. Okay? So now I'm trying to make a dot product with the function I got in the first function I got. Let's try to do this. D dot the first equation. What's gonna happen? I'm gonna copy this first equation with the Lagrangian multiplier. Okay. And since I'm doing dot products, I need to move some stuff. Okay. And then I'm doing dot products. But this is only the p component of the gradient, so I should recover it back to the original term. So I should do this. And I should do this. And I should do this. When this is happening, I cannot write in this format. I cannot write it in this form. So let's see. Oh yeah, this is right. This is right. Yes, this is right. Okay. So I just do a dot product, a pre-multiplication with d. Okay. So feasibility wants us to, let's remind ourselves, d dot D dot F. D dot F. Let me see. This part is always confusing. So I really need to talk about this again. Uh, D dot F negative. But right at the optimum. Right at the optimum. Uh, so sorry. This part will go later. Okay? We need to talk about what happened earlier. So if I have a contour, this is contour of F, and ah, we can, yeah, let's use the same example. So here is your xk, and here is already your optimum. So in the earlier example, and this is you can say is the D for k, right? So when we are trying to study from SK, then we said um, the contour here, the contour is going to be like this, right? So your gradient of f would be perpendicular to your um, contour of f. Gradient f is perpendicular to your contour of f. Okay, so this is the direction of f equals, right? Equals. So right at the optimal, so in this particular case, right at the optimal, if I try to move from away from the optimal, so you need to observe this. I need to zoom in. Okay, and let's say this is, this is your H I, right? And this is your optimal already. Then if you try the direction of your gradient, okay, if you if you are not sure whether that point is optimal, and let's say you try to move away from the optimal. So in this case, you may have deep movement this way or this way or this way. So there are three possible ways. If you move, if you move toward uh, this direction, closer to the same side of your gradient, then your dot product between them is positive. That what? That means gradient f movement. Let's see. Why is it positive? That side. Oh, okay, okay. It's not moving this way. Sorry. So yeah, no, it's hard. Uh, we need to show in this that if I try to have an increment from the optimum, then by Taylor expansion, you will have uh, location at the optimal, and then increment, and then dot product here. But since this is this is the optimal, right? So you should have the smallest function value already. So no matter what kind of increment you do, it will be larger than the optimal. So what does that mean? That means this term will be positive or zero. Okay. So earlier when we talk about this, this is about a discussion where we are still not at the optimal. So if we keep on doing this, we will keep on finding the smallest point. But when we reach at the optimal, when we stay on the optimal and we do Taylor expansion, this is the position with the lowest function value, and whatever increment you do, whatever movement you do, you may have function value that would be either the same or larger. Otherwise, this would not be the optimal, right? So if it's either the same or larger, then this term is either zero or positive. So from here, these are at the optimal. So this term is positive or zero. And we already show this term is negative, right? DGI. And for the feasibility, this is always zero. This is what's shown already. That remains the same. D gradient H equals to zero. It's always like that. So this part is important. You need to show that some terms inside this Lagrangian formulation would be positive or zero. Some terms will be negative or zero. Okay? Once you have this, you can you realize the only way this whole equation becomes zero is that you need to do something with your mu j. Okay? Because this is positive or zero all the time. This is zero all the time. This term is zero all the time. Here, it could be something uh, your mu j, if your mu is negative, then this term is either positive or zero. So this is positive or zero, this is positive or zero, then there will be chances that this equation will be positive. Can never be zero, right? So mu has to be positive, cannot be negative. There's only rule to make sure there's a chance this whole thing become equals to zero. So this indicates that mu j has to be positive. Okay, so that's why in the KKT condition there is this particular rule: mu j must equals to zero. Okay, now we have mu j sj equals to zero from the second. Mu j sj equals to zero. Let's now come back to mu j sj equals to zero. Oh, sorry, here is positive. So we now can have a discussion about mu j sj equals to zero. We also had gj plus sj squared equals to zero. That's at the beginning when we define slack variables. So there are only two possible cases. That is, Sj is zero or Sj is not zero, right? So when Sj is zero, the only possible case is that your Gj must be zero. But when Sj is not zero, combined together, when Sj is not zero, then your mu j has to be zero. So mu j Sj equals zero. So combining these two equations, you discuss all the possible cases, you end up with either mu j equals to zero or gj equals to zero. So it's an either or situation. So either both mu j or j equals zero, so you end up with a new equation which is mu j gj. So that's why for KKT condition there is this particular term. Okay, so combining everything together, your KKT. So basically, three of them: partial f partial x p plus summation I lambda I partial h I partial s p plus mu j gj x p equals to zero, and then mu j gj equals to zero, or the mu j positive. So that would be your KKT conclusion. Okay, so p goes from 1 to n. This is number of variables in x. Okay? And ij will be number of your constraints. Okay? That's the proof for KKT conditions. Do you have questions? Okay, so last time we talked about how we are handling nonlinear constraint optimization and the uh, first method we introduced is linear programming, and I showed you how you can use KKT condition to check whether the design point is optimal or not. Now, we didn't talk about a more advanced method. It's called quadratic programming. So now, since we already talked about KKT, we can now introduce quadratic programming. So earlier we talked about LP, and I shared with you how you can sequentially perform first order Taylor expansion to do sequential linear programming. For QP, you can also basically it's based on second order Taylor expansion, and you can sequentially perform second order Taylor expansion and then do QP. So it becomes sequential quadratic programming, SQP. MATLAB basically is having a SQP solver. Okay, so SQP is so commonly used in numerical optimization packages. So I think it would be good that if you can learn what's happening inside QP. Okay, so for QP, you have general forms in this way. This is the general form. Okay, so this is second order, and the other two are first order. So you can notice that for QP, we have second order Taylor expansion for the objective function, and we only have linear approximation for constraints. Both are zero. This is inequality, G inequality, H equality. For both G and H, they are linearized. Okay? So, also, for all the X, that it has to be positive. Okay? Now, how come the first equation looks like that? It's based on second order Taylor expansion. So I can show you second order Taylor extension of F looks like uh, okay, that's your second order Taylor expansion, right? So you will have a lot of constant terms. This is a constant. This term will be constant. constant terms. In optimization, you don't care about the constant terms in your ability function because they are constant values. No matter what your x changes, the constant values are still there. It doesn't change. So in order to find the optimal x, you don't care about the constant terms. Okay? And right here, basically, this would be your C. Okay? You do have a gradient dot product with x, so that's your C. And you also have x dot product with Asian dot product with x, so that would be this part, right? So all the constant terms has been negative. We don't care, but for the terms with x has been uh, placed in the ability function. Okay. Now let's take a look at the KKT condition of this. Since we already learned KKT, so let's take a look at the KKT condition. So first of all, we need to formulate Lagrangian. So here we officially tell you the first equation is called Lagrangian. You can write it as an L. So Lagrangian basically is F plus Lagrangian multiplier times your constraints. Okay? So what are our constraints? We have G, we have H, and here I am going to rewrite this particular equation. This one, rewrite it as a standard form. Negative x must be smaller than or equals to 0. Okay? And I'm going to apply Lagrangian multiply in front of every one of them. So I'm gonna use u, v, and w because there are too many constraints. So u is a vector, the product with g. V, the product with h. W, the product with negative x. So this term is called Lagrangian. Okay? And in the KKT condition, we want gradient of Lagrangian equals to 0. That the first equation of KKT implies gradient of Lagrangian equals to 0. So you can then end up with Asian times x plus c. So that would be the gradient of that, right? Gradient of that. And gradient of g ends up with a. So it's a matrix times u plus gradient of h. So you end up with a matrix of n times v. And the last one would be negative w. So this equals to 0. So let's check again. This is quadratic. So you have two of them. You have one of hx and the other one also hx. So two hx. So divided by 2, so it ends up with hx. Cx ends up with c only because of the derivative. G derivative ends up with A. A and then Lagrangian multiplier. Derivative of H ends up with N and multiplier of E. This is only negative X, so ends up with negative 1. So negative W. Okay? So that's the first equation of KKT. Now, what do we do? We also so this is KKT rule number 1. So for KKT rule number 2, Lagrangian multiplier times your inequality constraint equals to 0. So you will have this is your inequality constraint. So mu times g, this equals to 0. And also w x equals to 0. Right? Because the rule number 2. Okay? And also the Lagrangian multiplier in front of the inequality constraint must be positive or 0. So here, positive or 0. So this is KKT condition number 3. Okay? Now, here are some troublesome parts. This part and this part. Why they are troublesome? If you look at the equation, you end up with KKT number 1. You have a matrix Asian times your x. Okay? So Asian is basically a matrix with a lot of constant values times your variable. So it's like a coefficient times x1 plus coefficient plus x2, something like that. So this part, everything is linear. Similar to AU and NB. Don't be afraid of the A matrix and N matrix. They are just a bunch of coefficients. They are a bunch of coefficients. So when they multiply with your x, they are just a uh, linear combination of all the vector terms. But for u and g, u is a vector of your Lagrangian multiplier, g is a vector of your constraints, w vector of multipliers, x vector of variables. When two vectors dot product with each other, you end up with wx1 plus wx2 plus w3x3, right? And Lagrangian multipliers are also considered as variables. When you have variables multiplying with each other, it's like an x squared. They are nonlinear. So these two equations are nonlinear. So far, only these two terms are nonlinear. They are the troublesome part. We can put ax minus b back to this equation. It ends up with g equals to a x. Yes. ax minus b. Okay? So this just to show it's not unlimited. Okay? Because u times x is not unlimited. Okay? Now, can we try to make everything easier for handling? So here we are going to introduce select variable again. So we are going to introduce select variable. But this time we are only introducing in this form. A transpose x minus b. We're going to say s vector. We do that. And because the way we introduce select variable, we need select variable to be positive or zero. Otherwise, it won't be equivalent to the original constraint. Okay? So let's try to use this way and see if we can make this nonlinear behavior better. So when we do that, uh, we will have we can then plug back, plug in. So we end up with u and over here minus s equals to 0. Because ax minus b equals to negative s. Right? You just plug in, right? So we end up with uts equals to 0. That's also not linear. Still a problem. So even if we introduce select variable, we still end up with u s equals to 0. Okay. So we will just keep in mind we have these equations, and then at the end we'll put everything together and see what we can do. Okay. Now for the for all the select variables, we have u, v, and w. The rule for u, v, and w: u is the select variable for inequality. W is the select variable for inequality. So the rule is u and w has to be positive or zero. That's from KKT. Okay, but how about v? V is the not select variable, the Lagrange multiplier. U, W are Lagrange multipliers for inequality. The rules are they has to be positive or zero. But for the v, which is the select variable for equality, the KKT condition doesn't set out a rule for v. But when we, at the very beginning, when we talk about Lagrange multiplier, we said for equality constraints, the multiplier cannot be zero. Okay? So let's recall v cannot be zero. Because we want the gradient of f and the gradient of equality constraint parallel to each other. If the multiplier is zero, then that parallel behavior disappears. So this rule still has to be valid. Okay, so how can we introduce a trick so v is not zero? Here, we are going to define this. Okay, we define v equals to y minus z, two different vectors. So as long as y is not z, then v is not zero. Okay, and we define y and z in such a way so that y and z is always positive or zero. There are reasons why we do that, but this is how we define in such a way at this point. But y and z are not the same, so that's a way for you to make sure v is not zero. Okay. So what happened at this point? So let's collect everything to sum up. We have first equation, which is here. This is from first KKT. Okay. Then we have this equation. So this is G constraint with the introduction of select variable. And also we have this one. You don't need to do anything because it's given in a nice form. Okay. And what else? These are the non-linear equations. We do have some nonlinear equations, which is this one. And also this one. Okay. These two are nonlinear. Okay. And also we have many variables. So let's take a look at all the variables that we have. We have x, right? At the beginning. Then we have Lagrange multipliers. We have u. Oh, let me show you little bit here. We have. Let me try to do some color. Color here. X positive, right? X positive. So we have positive or zero variables. First one is x. Okay. Then we have slack variables. U positive or zero. How about v? We don't have v anymore. V has been converted to y and z, right? And we have w positive or zero. So we have u, v already converted to y and z, and W. Okay? What else do we have? We have select variables. They were defined to be positive or zero. Otherwise, it doesn't work. So they are new variables. They are all positive or zero. Okay? So can we write them down in a matrix form? Let's try it. Let's write them down in a matrix form. Okay. The first linear equation, h times x what times u, a times u. I forget about the transpose. Oh, I tend to write it in this way. The first one, h is here. A times u, a times u is. And then n times v. V is x minus z. So n here, negative n, right. And negative w, the third. So here is negative identity matrix. There is a plus c here, so negative c vector on the right hand side. And this one is here. What am I doing? H times x as the first term. C, move to right hand side, is just a vector of coefficients. A times u, A times u. N times v, v is y minus z. So n times y, negative n times z. Negative w, here, negative identity, so it's a 1, 1, 1, 1 diagonal term times w. So at the end, it's still done. Okay? Next, second equation, A transpose negative B becomes B on the right plus S, so fourth one, so plus identity. The other AX minus B plus S. AX identity times S. B goes right hand side, so positive B. Okay? Next, N transpose the E vector, the rest of it. So you notice that I can actually write down all the linear equations in such a big form. And let's just call this whole thing as big B matrix. Okay? And let's just call this big X vector. And let's just call this big D vector. So big B times big X equals to big D. It's a linear equation. Or you can write it in this way. Okay? And remember, all the X now will be positive or zero. And there's additional nonlinear terms. W X equals to zero and U S equals to zero. So all the kicking condition ends up with everything like this. So right here, these parts are very good for linear programming because they are linear equations and also all the variables are positive. So there is a way to solve it by linear programming. It's called the two-phase approach. There is a two-phase approach. So in phase one, you solve additional process. So here is like let's say you have a position. Actually, I think I can put the D on the right hand side. As long as they are positive. So here, must formulate everything properly to make sure D positive. Because in linear programming, we want all the coefficients on the right to be positive. If you have one equation that is having negative coefficient, just multiply it minus 1. Then that particular line settles. Right? So in the two-phase approach, here, what is big one? It's actually all the basic variables. And they are non-basic at the beginning. Okay, and of course, all the x and y are positive. Okay, so you just solve this additional like a phase one approach, and you will be introducing new variables. They are basic variables. And then you apply linear programming, you will end up with some optimal solution. And the goal is, at the end, all of your basic variables become zero. So if you can find the optimal of this phase 1. Initially, these parts are 0, so all of your basic variables basically equals to the d parameters you have. But after several iterations of linear programming, they become non-basic. So x will become basic. So the goal is this part becomes 0. When you reach to the optimal and this part becomes 0, this part becomes 0, you will end up with a bunch of x that satisfy dx equals to d. So you will use this trick. You can find a bunch of x that satisfy this equation. And because of linear programming, x are always positive and 0. So this is always satisfied. So all you need to do next is to make sure whatever you found in phase 1 satisfy these two rules, then that's out. Okay? So from the very beginning of QP, we have the only difference between QP and LP is that you have second order terms in the objective function. And also you have inequality constraints. With all these derivations, you end up with a big chunk of matrix. You end up with this. You need to satisfy this. So you are sure that's the answer. Okay? So, because these derive from KKT. Now, even with this big matrix, we still don't know what the optimal of x. You cannot just inverse B and put it on the right because this B is not a square matrix. You cannot use least square approximation, try to make approximation, it may not be the right solution. So one way to solve this is to use this two-phase approach. It helps you to find feasible solutions of x that satisfy dx equals to d. Okay? So that's a very interesting way to solve QP. Okay? So what if, after this linear programming, at the end, you found something and then it doesn't satisfy the two nonlinear terms? What do you do? You can sequentially perform this. At the end, if you can find everything right, then you should be able to find the solution. Okay? So that's quadratic programming. Okay? I forget to record the screen. So today only this. Okay. Now I would like to introduce a meta code, FMICA. So it has a SQP solver inside. Let me show you FMICA. Okay. So trying hard to open up. Okay. I cannot show you very long thing first. So I will do it here and then open a new script. So how to start? So I always start with clear CLC and close all. And here, in order to do admin count, I can show you you can go to help and say admin count. It will give you the syntax. You can do this one. Okay? So eventually you are looking for this particular line to use admin count. So here I would like to write down my functions in a separate file. This is what I usually do. So all I need to do here is to define x. So I'm gonna say iter equals to 1. That's my iteration number. And I'm gonna say small case x. Let's work with a 2D problem. So vertical vector. So column and meter. So that would be my initial gas. Let's say 5 and 5. Okay. So vertical 5 and 5. Then I'm gonna, yeah, I think if I define my functions here, that's fine. So if I my x, do I define in a symbolic way? Okay, let's do it in a symbolic way. So f equals to x1 squared plus 10 times x2 squared. Something like that. And I can have a bunch of g functions. I'm gonna define it as cells. Okay? cells. So first one, I'm gonna say something like this. So x2 smaller than some stroke like this. So now I'm having something like this. I don't know contour because it comes down. So I need one line like that. So let's say minus 3x1 plus 10, something like this. So I need to write it in such a way minus x2 plus. So this is my first constraint, Coleman's line. So this must be smaller than 0. The other one, so this one is like this. Sorry, larger, larger. So I should make it times net minus 1. So 0, 0 plug in, it's a negative. Sorry, I was wrong. I was confused by myself. I want the logic. Use logic. Yep. So this goes to the. Yeah. So this goes to right. Negative x2. Yep. I was right. So here, then this is negative. Okay. The other one I can use similar equation, but this is for example 4 times. Okay. So I have two constraints. Okay. I can define the plotting zone 0 to 10, 0 to 10. So that would be my also design space. So I can say easy contour F and zone. And then I can say hold on x is equal. And then I can plot the two equations. So easy plot G, I can use a for loop for I equals 1 to number of G. And then easy plot G function inside the zone. Then, right? Sorry. Bracket. Let's try to do it. So, um, okay. So I want these two lines to be thicker, so I can say I can put a handle and set H. I better not use H. Let me use P. P as a handle. Set P line width as 2. So these two lines are my uh, boundaries. On the upper right corner, that's feasible space. And by observation, the solution will be somewhere here, right? Last time I think I also used this example. I tried to use KKT to check. I was trying to check the intersection point, but actually not yet. So anyway, let's use this as an example and try to use that mean count to solve it. So how to solve it? How to use that mean count? Here you can say uh, basically. So you don't really need x iter. You don't need iter. So iteration is inside mean count. So let's just call this x0. So x star basically optimal equals to f mean count. And here I'm gonna call my func, so my function. And then x0, do you have a and b? What is a and b? So basically, it allows you to do linear programming. Ax smaller than b, or ax equals to b, equality constraint or not inequality. But here we are not, we don't use that. We directly just put an empty input here, treat ABs as empty input, but the lower bound and upper bound we need to. So lower bound would be zone 1 and 3, and I need to make sure here I'm using, let me use horizontal vectors. So zone is also horizontal. Zone 2 and 4. I'll check if it's on. Uh, so get back here. The first one and the third. Second one and the fourth. Okay? What's next? So this is lower bound and upper bound. Then we need to give all the nonlinear constraints. So here I'm gonna say my constraint. So I'm going to write down all the functions and constraints in a separate file. Okay? And then I'm gonna use so-called options. Later on, we need to define options. Let's do options first. So how do you do options? So you can click on the here, or you can just search options. Here, optim options. So click on optim options. Okay, this is where you can define some settings for your fmin options. So here, opting options. Okay, so for fmin, what do you want to do? I would like to choose my algorithm. So algorithm, and then use SQB. SQB. Okay, and then there is something called iteration. I think. Display. Display. So for the display, by default it's final. It only shows the final iteration. So I'm gonna change it to iter. Display, change it to iter. So it will show you the iteration process. Okay. So what's missing is what is my comp, what is my func. So you need to save this file for now. Open another script. So here's a function y equals to my func x. Save it. Save the file name as my function. Okay? And then in your main file, here's your function, right? Copy it to my function. So here in fmcom, if you read an external file, you have to only allow single variable x. So right here, x1, it has to be x bracket 1. x2 becomes x bracket 2. And then return the function value 1. So save. So it's one way to describe your functions in a second file. So later on, when your problem becomes more and more complicated, you can formulate your functions outside of your main code. It's like a second separate code. Okay? And also open another file. Here, I'm gonna copy all these, but now define a different code. Here I'm gonna call C and CEQ and call this one com X. Why C and CEQ? C represent constraint value. So if you go back to MATLAB as Mecon description, find CEQ, you can see that you can write down C and CEQ in a separate file. This is a separate file. Okay, so C represent the constraint function values of all the inequality functions. So now we have two inequalities, these two. Just copy them here. Okay, but two lines. So they will become two values. But like I said, for additional constraint function, MATLAB only allow one symbol for the variable. So you need to use x bracket 1, x bracket 2 to specify each function value. So for the CEQ, just give an empty output. So no equality constraint. Save the file as my com. Come back here. In addition to it. What did it do? Takes over. Okay. Really? This is wrong. Okay, then you can do it. So that's the optimization process, but you cannot see it, right? So what can you do to see it? You can, every time you goes into this fmcom, will call the function values. We call this file. Every time you come here, you plot out the position. So you can say plot x1 and x2 with a small red circle. Okay? Marker size, let's say 5. Let's see. Okay, not clear enough. So maybe I will make a line width 2. Okay. So from here, you can see MATLAB try to move around the design space and then find a point here. But let's try to pause whenever plots. Just pause a little bit because it's too fast. Have a second. Sorry, not pause. Let's say draw now. It's, draw now and pause. Because MATLAB tends to do the computation first and then draw in one, in all together. So if you call draw now, it will make the drawing. Okay, now. So we can see how the design point try to move around and then eventually find the point right here. Okay, so let me show you something interesting. What happens if I zoom in? If I zoom in here, that's the position of our initial guess. We keep on zooming. Oh, something strange here. How come we have 3 points? So MATLAB is trying to do finite difference. MATLAB move forward, compute function value, move up, compute function value, use the function value difference to determine the gradient. So even for MATLAB, it is numerically evaluating the gradient. Okay? So it doesn't only stay there, you actually try to move a little bit to compute for gradient. Then, in the first iteration, you move up to here. We can, it's at the corner. Let's just observe another point right here. This one. Come on. Come on. Okay. Something weird. We run. Okay. Let me zoom in at one of the design points again. Here. It is also doing minor difference. A little bit increment toward right, a little bit increment toward up. And that's how MATLAB is doing. And now let's take a look at the iteration process. Uh, so what is your X star? It's a 3.8, 1.5. So this particular one. That's the other one. 3.8, 1.5. And during the iteration process, they actually tell you the function count 3 times every time. How come it's 3 times? The current point, 1 point toward right, 1 point toward up. So every iteration we did 3 function evaluations to find the gradient and then apply S2P. Okay? So feasibility 0, some value close to 0, 0, something close to 0. Okay, feasibility has to be 0, so it's feasible, right? And optimality positive, oh, close to 0. So the optimal complete. Let's try to add some equality constraint. If I say if I have some kind of equality constraint, h equals to some kind of like a circle. How about a circle? So x1 squared plus x2 squared minus, let me see how long, 3.5, 3.5 squared. So it's a circle. So I need to draw the circle. Easy plot h in the zone and assign a handle, set up the drawing style. Maybe make it red color, maybe green color. Okay, and also copy this to my constraint function. So here I do have one additional constraint. And solve, see what happens. Okay, I think converge. 5 iterations. So if you take a look, if I zoom in, let me kind of try to find a point that stays on top of the green curve and also inside the upper right region. So actually, this is the optimal point. Okay, this is optimal point. Position is 3 and 1.74. So x star equals to 3, 1.74. Okay, so from here you can see FMICON was able to handle both equality constraints and inequality constraints. Also nonlinear constraints, nonlinear objective functions. Okay. Let's try to make the objective function. I think that's fine. So this is SQL. Okay, let's try a different solver. So if you take a look at MATLAB's solver, so there is a method called interior point. Okay, so it's a different solver. Different solver. So if I update here to this interior point method, different method, and try to solve it. Okay. You can see how different solver handles the iteration process differently. So it took longer iteration, but still was able to find a solution. Okay? So in your project, when you try to find some kind of problem, you also need to figure out what kind of solver you're going to use. You can use MATLAB, you can use Python, you can use whatever. Okay, and uh, I know many of you may want to use GA, genetic algorithm. I hope not all of you use GA. GA is a very simple method, and I would recommend you to use it only if you need to use it, because GA requires more function evaluations. If you use gradient-based approach, overall, you only took 32 function evaluations. It's a very small amount of function evaluation. If you use GA, solve the same problem, you may need to have 1,000 function evaluations. So for practical engineering problems, if you use GA, it's very time costly. So usually GA is used for some other purpose. So that's it for today. I will share this code with you and my notes. Uh, for the course schedule, I already modified. We already passed all these lectures. Okay. So next week is actually our proposal presentation. I will introduce GA later because our progress is slightly delayed. So I will talk about. I guess I will use special numbers. Everything here. And then GA2. Okay. So today is a continuation of KKT and QP. Okay. So next week we have proposal, and 2 weeks from now, that's my travel. I have business for travel conference. So we will have an exam. I will skip QP. Okay. So in the exam 2, you need to do linear programming and KKT. Okay. And I will talk about GA in 18th. And if I think I will still have time, I can talk about some of the special topics. So let's talk about the grouping. Uh, let me do let's check everyone's here. So Yichen, okay. So Giovanna, is he dropping? Is she dropping? I guess. So let me just. Zhiwen, 自文，哦，易安，就是子炫，是给马图东，抓了，秋明，我宽，少，陈奇，安佑，林志，简易，对，Louis, dropping? Not sure. Federico, Israel. 博远. So we have some groups that doesn't have enough students. So, Zishun, can you work with Wu? Can you raise your hand? Yeah. Because you two are only one student left. So I think we can do this. So we have 2 people per group. Okay. So if Louis also drop, then Xian Yi, you just walk by yourself. or let's see. Or this is maybe you can. Let's try. Do you know anyone? Do you know any student? Okay, so maybe I just randomly, because I'm not sure if Louis is here. So I will just let's assign to the first group. How about that? Just assume he's drunk. He's dropping. He will stay. Okay, then let's recover. Yeah. So you know him? Can you? So his teammates, right? Please help him to communicate with Bruce. Okay. Okay. Well, I think we can still do this. So next week, when you do the proposal, how does a proposal look like? So, proposal. So basically, it's a PPT. You need to submit a PPT file, and you can talk about basically introduction of the problem, and then talk about functions and variables. Okay, and you can talk about your optimization foundation. Okay, so all kinds of functions can be either objective or constraint. So let us know what kind of problem you're going to solve, and then introduce the solver. What kind of method you are proposing to use. I will recommend you to use a new method. So learn from internet, books, papers, AI, that's fine. Okay. And try to avoid GA. And uh, simulated annealing. Because they are two very common methods, especially for Taiwanese. If you Google optimization, the two simplest method it will show pop up is GA and simulated. Try to avoid them. Okay? Try to learn something new. Okay, and you can also mention what's your expectation or expected results. Something like that. Okay. Uh, so please work with your teammates. It's an important part of the lecture. Okay. That's it for today. If you have questions, you can stay or come in. Okay. Thank you. Bye bye.